Dear students, in this section, we will see one more problem type belongs to greedy approach called optimal tree problem for encoding. Now we'll see what is encoding and how optimal tree is useful for encoding of character in a test. What is optimal tree problem? Suppose we have to encode a text that comprises character from some n character alphabet, but by assigning to each of the test characters some sequence of bits called code word. This is a very familiar topic already studied in data communication or computer network. That is called encoding. We want to, if you want to encode a text, that is, we are encoding each character in a text with some code word, some binary prefix codes, and each code word is called a code. That is a sequence of code is called a code word. There are two types of encoding techniques usually used to encode the characters of text. That is, first one is a fixed length encoding, and another one is variable length encoding. The fixed length encoding, this method assigns to each character a bit string of the same length m. So normally, if n is the number of character in a text, so that is m is equal to greater than or equal to log n base 2. Log n base 2, that normally the length of that is code word, that fixed length. It is a fixed length for each and every characters of a text that has the same length, that is called a fixed length. And another type of encoding is called the variable length encoding. This meant the name indicates this meant assigns code words of different lengths to different characters. And there are different techniques for encoding the text using both fixed length encoding and variable length encoding. Today, in this section, we will see one technique, one famous algorithm that is called Huffman encoding techniques for encoding characters of a characters in a text. So it is variable length encoding. This technique is so again, if you want to create a binary prefix code for some alphabet, it is natural to associate the alphabet's characters with leaves of a binary tree in which all the left edges are labeled by 0 and all the right edges are labeled by 1, or it is vice versa. So that is, if we assume that in the binary prefix code, so we are using a binary tree for encoding, and each node indicates one alphabets. And if there are 5 alphabets in a text, 5 different characters in a text, then there are 5 nodes. That is, a binary tree contain 5 nodes. And what we are using, the left edges are labeled with the zeros and right edges are labeled with 1, or vice versa. You can left edges you can label with 1 and right edges are you can label with 0, but you have to follow the same uh, procedure or same method. The code word of a character can be obtained by recording the labels on the simple path from the root to the character's leaf. It's idea. So once we label, so we find the code word for each character. So record from, that is, from root to that particular character. That is, if it is left and right, so it is left and right 0 and 1. So it is, we will see with an example. Since there is no simple path of a leaf that continues to another leaf, no code word can be prefix of another code word. Hence, any such tree yields a prefix words. That indicates that all the code words are different. There is no chance of same code word for two characters in a binary tree. So we will see Huffman trees and codes, how Huffman uh, Huffman proposed encoding of, that is uh, that is code word for each of the character in a text. Among the many trees that can be constructed in this manner for a given alphabet with the non-frequencies of the character occurrences, construction of such a tree that would assign shorter bit strings to high frequency characters and longer ones to low frequency character can be done by the following greedy algorithm invented by David Huffman. So what we are doing here, Huffman proposed one algorithm that is called David Huffman, that is David Huffman's algorithm. What he says, each node, inside each node, uh, we put the weight, that is a frequency, so occurrence of frequency weights, and outside that is the label name. And uh, he is suggest what he is idea behind his algorithm is, that is assign shorter bit string to high frequency characters and longer ones to that is longer bit strings to low frequency character. So this is the idea behind the Huffman um, algorithm. So we'll see the algorithm that is in steps. Initialize n one node trees and label them with the characters of the alphabet. So he says if there are n characters we want to encode, that is in a test or in a, we are using total n characters. So we first what we are initializing n nodes with, and labels them with the characters of the alphabet. Label, that is label each node with their character alphabet. Record the frequency of each character in its tree's root to indicate the tree's weight. So inside the node write the frequency or its root with the, that is it's each root indicates its frequency, that is its weight. More generally, the weight of a tree will be equal to the sum of the frequencies in the tree leaves, so that we will see. So that is a tree containing one root and two left and right, one left and one right child. So the left and right child, that is each left and right child, there is a there are two indicates, there are two, but there are these are the two nodes, these are the two leaf nodes, these are two characters. So each character is associated with one frequency weight. So the sum, these are root of these leaf node, the frequency of that is equal to, that is equal to the sum of these frequencies, sum of the frequencies of the left and left right child. So the second step, repeat the following operations until a single tree is obtained. Find two trees with the smallest weight. Make them the left and right subtree of a new tree and record the sum of their weights in the root of the new tree as its weights. So the Huffman suggests among all the frequency of all the characters, find the two character with the low frequencies, and then you combine this and find true with the smallest weights, make them the left and right subtree of a new tree. Create a new tree with these two subtrees and left and right subtree, and record the sum of their weights in the root of the new tree as its weights. So we'll see with an example this. A tree constructed by the above algorithm is called Huffman tree. It defines in the manner described by Huffman code. So this is an example how Huffman tree code word is generated. Consider the five symbol alphabet A, B, C, D and underscore with the following occurrence frequencies in a test made up of these symbols. So there are five symbols we consider here, A, B, C, D and underscore, and the frequency associated with each symbol. A is equal to 0.35, B is equal to 0.1, C is equal to 0.2, D is equal to 0.2 and underscore is 0.15. So the Huffman tree construction for the above problem is shown below. So what we are doing for each, that is A, B, C, D, that is a frequency weight is associated with A, B, C, D. Now what happened now? So this is a low frequency we consider first. So low frequency, that is the first consider the low frequency characters. Low frequency character among these is equal to 0.1. So 0.1, B is a 0.1. Now you see that is equal to, this is a node, this is a node 0.1. Now next is go to, next is go to 0.15. So this is underscore 0.15. Now it next is go to C or D, and from as that is it appears in the list that is C is first, so C we consider C, and next is equal to D, and the last one is A, because the 3.35 is the frequency. Now you add this all, you will get 1, right? This is equal to 100%. So but we can say the frequency occurrence of these all equal to 100%. So this is 0.1%, 10%, this we can say 15%, 20%, 20%, and 35%. Now among this, Huffman algorithm suggests find two alphabet low frequencies and make a new tree uh, with the sum of the weights assigned to the new tree root. Now B and underscore, these are the two lower frequency characters, so B and C underscore, so zero point 0.1 and 0.01 0.15. So add this and create a new tree. So this is a tree with a single node, this is a tree with a single node, so this is adding this zero point 0.1 and 0.15, this is going to 0.25. So this is a tree. Now this is a tree 0.25. Now again, so find the next two low frequency characters, zero point 0.2 and zero point 0.2, so C and D. So C and D, and make another tree with the new root with a weight, that is sum of frequencies of the left and right, so it is equal to 0.4. Now you see that is equal to 0.25, this is the sum is 0.25, and again we are arranging 0.25 here, and point A is also remaining, that is A is equal to 0.35 and 0.04. Now among these three find the lowest two frequencies, so 0.25 and 0.35. So this is go to, now what happened, these two you combine it, so 0.25 and 0.35, that is go to 0.6, right? So now that is we have the zero point 0.4, this is a sum of the C and D, so and 0.6. Now again you arrange it, that is in ascending order. Now the 0.4 and 0.6, so you combine it, so this is the left of, that is the left of the tree is go to C and D, and this is go to right subtree containing this part 0.6. Now so we constructed the tree, this is the tree what we constructed according to the Huffman algorithms. And now what we have to do, that is you label each left edge with zeros and right edges with 1. So left of this, that is 1.0 to 0.4 equal to 0, right? 0.4 node 2, that is C equal to, that is equal to 0. So and right of this 1.10, and this 0.42, that is a D, so from here the right child is equal to 1. So here similarly for right is 1, left is 0, right is equal to 1, left is equal to 0. So now the leaf node indicates the characters, so CD B underscore, and this non-leaf node indicate the sum of the weights of this two characters, each two characters. So it is binary tree, now you see that is go to if you want to code it, if that is the what is the code word for C, the code word of C is go to 0 0 0 0 is the code word for C, and similarly 0 1 is a code word for D. Similarly 1 0 0 is a code word for, that is B, and 1 0 1 is a code word for underscore, and 1 and 1 is the code word for A. Now that is in the beginning I told Huffman, what Huffman says, that is high frequency bits, high frequency characters are assigned with lower bit strings and shorter bit strings, right? And lower characters, the lower frequency characters are assigned with a longer bit string or bit code. So now we see in this case the lower, that is equal to B is the lower frequency character, so B is equal to, that is the, it should be longer bit code, that is equal to 101 100, and again that is go to underscore, is again that underscore is the next one, so 101. So these are the first two lower bit scores. Now next is go to what? Next is go to point to point C and D. So C and D what we see? So 0 0 is C and 0 1. There are two bits are used and here it is three bits are used, and now is go to next is go to 3.5. Also there are two bits are used. Two bits are used. So this is a so same Huffman tree with the labels and frequencies. Labels and frequencies. The resulting code word as shown below. So that is the same frequency and code word. That is 0.311. B is equal to 100. C is equal to 00. D is equal to 01, and underscore is equal to 101. So now using this, that is we want to that is encode, that is the word dad, dad is encoded as, that is equal to d value. What is the d is equal to 01. A is equal to what? A is equal to 1 1, the next two character, and D is again 0 1. So this is one. And that is bad underscore AD, that is equal to, we can, that is B, but B is equal to what? B is equal to 100, that 3, and A is equal to what? 1 1, and D is again 0 1, 0 1, and underscore is equal to 101, and A is equal to 1 1, and D is equal to 0 1, 0 1. So this is each and every any word we can with the help of any word that consists ABCD underscore we can encode. So this is called the Huffman encoding. So with the occurrence of frequencies given and the code word length obtained, the average number of bits per symbol in this code is. So what is the average number of bits per bits per symbol? So average number of bits per symbol is that equal to add this 2 plus 3 5 plus, that is equal to, we can add it, and so we can 2 into 0.35, 2 into 0.35 plus 3 into 0.1 plus 2 into 0.2 plus 2 into 0.2 plus 3 into 0.1, and all this you add it, you will get 2.25. So what you understood from this, we used a fixed length encoding for the, if we have used, if we would have used a fixed length encoding, so same for the same alphabet, we would have to use at least 3 bits per each symbol, right? So had we used a fixed length encoding for the same alphabet for this, and if we would have to use at least 3 bits per each symbol, because that is there are 5 characters, definitely we have to use 3 bits per. So for this example, Huffman code achieves the compression ratio, a standard measure of compression algorithm effectiveness. So it is there is that is Huffman, that is code or Huffman algorithm suggests that is improve the compression ratio. So you can see that is a compression ratio 3 point, that is if that is in a variable length encoding, that is each character equals 3. So 3 plus 3 plus 3 plus 3. So you can see that is go to, that is 5 into 5 into 3, 5 plus 5 into 3 15 divided by 3, that is go to 3, right? But in this case that is go to 2.2. So what is the compression ratio? So 3 minus 2.25 divided by 3 into 100. So what will get 25%. So in other words, Huffman encoding of the above test will be used 25% less memory than its fixed length encoding. This is the advantage of the Huffman encoding. This is the advantage of the Huffman encoding. So for any characters in a test with frequencies available, we can use Huffman encoding technique, and it is very useful, and the compression ratio is uh, that is improved compression ratio, and because that is for each character it use different code word, and it is unlike that is a fixed length encoding, it is a more better technique, but that we can say that is a better technique for encoding the character in a test.